All right, so we're just going to go over a few like topics that we've done throughout the exam or throughout the course. The first one that we were going to do is just naming rules. So for naming rules, we have like 10 different prefixes that we can put. I know this is like super rudimentary, but so just in order, we have like the methane and then ethyl, propane, butane, pent, and then hex, hept, oct, non, and dec. It's important to be able to really go from like a name to a structure really fast, because on the exam, you'll see a lot of questions that are like, cyclobutane reacts with like HSO4, find what is the name of the product. That kind of stuff will be on there a lot, anything like that. Or another thing you'll see is a lot of condensed drawings from going from condensed to the actual reaction that you're doing, which is also going to be something you'll see. So being able to convert those kind of things really quickly is going to be important, especially because you can't even, unless you change things, you can't write on the exam. As far as naming, we have like our 3 regular naming groups that we can do of alkanes, alkenes, and alkynes, which just means that it has a single bond, a double, or a triple bond. And then just going through our prefixes like we did. The 3 functional groups you'll see in all of Organic Chemistry 1, or need to recognize at least, are going to be like an ether. So it'll be an oxygen on both sides with like carbon groups. So you could have methyl on one side and ethyl on the other, or you could have a cyclo ether where you're going to have a full ring around it, and that would look like this. So you could even have like a cycloether that you're reacting something with. There's a bunch, but the goal of an ether, or the point of an ether, is just that you're going to have 2 carbon groups on either side. Alcohol is another one. It's just going to be an OH group anywhere. So you'll see it in something like the example that we'll be doing down here, stuff like that. The third one you'll see is an amine. So it's N grouped to carbon groups or even H's. So you could have an amine which is N with 2 carbon groups attached to your part, as well as just NH2 or NH with 1 carbon. All those are amines. So just look out for that kind of stuff. Also, the priority is going to matter when you're naming. So you want to make sure that as you're numbering your carbons, you're hitting the #1 priority first as you're going down. She said in class, as you guys, some of you I'm sure remember, that these 2 are really the first 2 that are going to matter, and then the rest of these kind of just fall together. So whether you're looking at all those, it'll be only semi-important to see which one of those will take your priority in that situation. So we're just going to practice a few of these. So we're going to name just these 2. So I'll give you guys like 2 minutes to name them both. And then when someone has them, just like put a thumbs up or in the chat or like anything like that. All right. Looks like some people got it, so I'll just start going through the first one. Yeah, so the first step in all these is to start numbering your carbons, at least in the first one. So in the first one, it just happens to be in this one that we're going to go from left to right, but we're trying to hit our top priority group first. So if I'm debating on whether to start over here or somewhere over here, I need to know if I go 1, 2, 3, 4, 5, and then 6, or if I say 1, 2, 3, 4, 5, 6, I'm going to hit my alcohol first if I use the red one. So that's what we'll use. And then the name will start off with, we know the end is going to be a hex because we have a 6 carbon chain as our longest chain. We also know that we have a alcohol group on 3 and a methyl group on 5. Because the alcohol group is the highest priority, we're going to end our name with that OL ending. So we know it will be at the very end that 3 all, and that's because the alcohol is on our 3rd carbon and we have to indicate that. We also, when we're doing that, we want to drop the A and E if we're using the all ending. So we'll take off the A and E and add that OL. If I'm adding, then we know I also have a methyl group on this carbon 5, so we'll add that too. So it'll be 5 methyl. And then we don't even have to add a dash there because that was our only substituent. So it'll be 5 methyl 3 or hexane 3 all. And then the second one, the first step that we need to do is draw out our group. So I'm going to start on this side and go CH3, CH2 is going to be here, and then CH2 is here, and then I have 2 CH3 groups coming off. So CH3, CH2, CH2, and then 2 CH3s on the end. Now I need to figure out my numbering. So we want to make sure that our numbering is going to be in the, we're going to hit all of our substituents or priority group first. So in this one, we just have a regular alkane. So we don't really have any that's the top priority. And I'll just start where I'm going to hit my first substituent first. So it'll be 1, 2, 3, 4. If you start up here, it'll be the same thing. In this case, we know it's going to be butane is going to be my ending because I have 4. So butane. And I have a methyl group on my 2nd carbon. So 2-methyl butane will be my name for that one. And again, that's important. A lot of your questions on the exam will have like this chain instead to start it off, and then you'll have to go from there to do your reaction. The next topic we kind of covered in class was boiling point. So the trend with boiling point is increasing with carbons and decreasing with branching, and then also increasing with hydrogen bonding. So if you're looking to see out of which like structure or molecule has the highest boiling point, the first thing you want to find is to see what the one with most carbons has, or if you have a functional group, what functional group you have. For these two, we're looking at the boiling point of these, and then we're going to count. The first thing we want to do, they don't have any functional groups, so we don't have to worry about that, but we want to count the number of carbons. So it'd be 1, 2, 3, 4, and then 5. And then on this one, it'd be 1, 2, 3, 4, and 5. So they both have the same number of carbons, so we can compare them. And does anyone know which one would have the higher boiling point?
The second one, because it has more like substituents.
So that's close. You're right on the right track to say that the second one has more substituents, but it means the opposite of what you had said. Our trend is increasing with carbons and decreasing with branching. So if I look at this, you're right. It has more substituents, which is more branched out than this one. So actually, in this case, this would have our lower boiling point because it's like less stable. I did have, someone had asked about this one. on, I put hex 3 all, not 3 hexan 3 all. The reason that is because if you're adding the alcohol, like the OL group right afterwards, it would be hexanol. So I'll give you an example of that. It would be something like this. I will say you won't run into this problem because it wouldn't show up on the open-ended probably. You would see a multiple choice and both of these won't be options. But if you had something like this, where the alcohol is in the number 1 spot, that's where you, in this case, you don't have to say like 3 all because hexanol is assumed. So I could write in this case, this is 1, 2, 3, 4, 5 carbons. I could say pentanol. In this case, that would be correct. I could say 1 pentanol, and that would be correct. But if I want to cut it off early, then I would do this: pentan dash 1 dash all, and then that would be the correct. So if you're dropping the A and E, or if you're adding that at the end, you're going to drop the A and E. But if you want to do it the other way, you can do that as well. Another form of the correct answer for this would be, if I was doing this top one, I mean, is I could do this and make it 3 hexanol. That would also be correct. So one thing you want to be like, make sure on the exam is just be prepared to see things in a different way than you might expect. But that's why you would cut that off. However, the other thing, going back to boiling point, the other thing you could have is something with a substituent. So now if I use these same 2, and I know before we had this one is our higher boiling point. If I start to add a functional group, now am I going to have my left one or my right one have the highest boiling point? It would be this one. The reason that is I have my 2 hydrogens on here, which is both a hydrogen bond donor and acceptor. So we know from H's, or we know from functional groups that, especially nitrogen, that it's going to have a lone pair, and then in this case, 2 hydrogens and a carbon on the other end over here. So in this case, we know that it's a hydrogen bond donor because it has H's, and an acceptor because it has a lone pair that it can use to accept more hydrogens coming onto the molecule. So in that case, because of that, because of this hydrogen bonding that's happening over here, we would have this have a higher boiling point than this because this has hydrogen bonding. So as far as donors and sectors, we're going to do another one that involves that. So an H-bond donor is anything that has a hydrogen to donate. H-bond acceptors have lone pairs to accept. So if I was looking at this one, I know this one was an acceptor because of my lone pairs, and it was also a donor because it had the H's. So now if we look at this molecule, how many hydrogen bond or donors does it have? How many hydrogen bond acceptors does it have? So I'll give you guys another second and to look over this one, and then how many, just let me know when some people have found the answer. So in this molecule, we're going to have a few of each, actually. As far as acceptors go, we're looking for anything that just has lone pairs that it can accept. And then donors acceptors will have both. So on this oxygen, this ether, every ether is going to be an acceptor only, just because the idea of an ether is having two carbons on both sides, and that's it. So this ether over here has lone pairs, and it can accept a hydrogen. So that'll be one acceptor for us. And then if I come around to this sulfur over here, this is also an acceptor because it has lone pairs that it can use to accept more hydrogens. So that'll be a second one. If we keep moving around, we have our nitrogen up here, and then this one just has lone pairs to accept as well. So that's going to be an acceptor as well. And then over here, I have another nitrogen that also has lone pairs. So that will be one more. As far as donors go, now we're looking for just things, just molecules that have hydrogens available to donate. So if I go back to this oxygen, I'm just attached to a carbon over here and a carbon over here. There's not a hydrogen that it's available to donate. And I'm talking about just the hydrogens on an atom itself. So ones that could be on here and on here don't count. Then I'm looking at something like sulfur in this spot. So here I do have a hydrogen that I can donate. So in this case, I'm going to have a 1H donor. Coming up to the nitrogen, I don't have any hydrogens there, so I won't have a donor there. And then over here, I do have hydrogen, so I will have a donor there. So in this case, I have 2 donors and 4 acceptors. As for constitutional isomers, these are molecules that are the same molecular formula, but have different connectivity. So if I'm looking at these, there's a few ways I can tell. My first check is to write the chemical formula. So I'm looking through these 3 to find which 2 are constitutional isomers. So we'll get that into a second. We'll just do a quick example. So if I'm looking at this one and then this one, I'm going to write the molecular formula for both. So this top one, I have CH3, CH2, CH2, CH3. So that's C4, 3, 4, 5, 6, 7, 10, H10. And over here, I have one CH3, CH, CH2, CH2. So here I have C4, and then 2, 4, 5, 6, 7, 8. Here I just have 8 hydrogens. So C4H8 is not going to be the same as this. So these are not constitutional isomers. They're a different molecule. However, if I did have this molecule, 1, 2, 3, no. Now we can check again. I have CH in the middle, and then CH3, CH3, CH3. So that's 3, 6, 9, 10 hydrogens and another 4 carbons. So these 2 are going to be constitutional isomers. So now based off of these 3, which of these are constitutional isomers? And then just let me know when anybody finds it. Yeah, okay. So someone said the first two. So if I do these, I see CH3, CH2, 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 and CH3. So that's 1, 2, 3, 4, 5 carbons, and 3, 6, 8, 12 hydrogens. Now, if I look at this one, I have CH3, CH2, CH, CH3, and CH3. This one's also 5 and also 12 hydrogens. Then when I look at this one, I have CH2, 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 CH, and CH3. In this case, I still have my 6 carbons. I'm sorry, my 5 carbons, but I only have 10 hydrogens. And that's because this ring here actually makes it so that there would be less hydrogens because there's less available space for a hydrogen to attach. Now we're going to get into the fun stuff with stereochemistry. So I kind of listed as just a wedge is always going to be toward you and a dash is going to be away from you. I also meant to draw this further down, but this is going to be our chair conformation every single time. So we always will have an axial up here and then equatorial down, then axial up, equatorial up, axial down, and so on as we go around. So this will be your chair conformation every single time if you're trying to decide where to put something on the chair. So I'll move that down in just a second. But so now we're looking for chiral centers. So a chiral center is going to be something that has 4 different groups. Groups attached to it. So if I'm looking at a molecule that looks like this, and then I see a OH here and a hydrogen, I'm going to look at what are my 4 groups attached on this carbon. So if I come up here to the top, to the OH, I have 1. So 1 group. And then H over here, that's different than both of these two. So second group. And now I come down to this one. This is CH3. But I also have, or it's carbon attached to the rearrangements. I also have another carbon on this side that is CH2. But our question is whether this carbon over here and this carbon over here are different or the same group. So even though they're the same molecule, we always want to take it a step further to check to make sure if they have the same things attached to them. So in this case, my carbon is attached to 3 hydrogens. But over here, I'm attached to a hydrogen, and a CH3. So that's different than being attached to 3 hydrogens. So in that case, I have my 3rd group over here and my 4th group over here, meaning that this is going to be a chiral center. So this molecule is chiral. If I'm looking at these ones though, now we're looking at just which of these 4 has a chiral center. So I'll wait again for a little bit so that people can kind of look into them and see which ones have chiral centers and which ones don't. All right, so let's take a look at these. So if I am gonna start addressing to see if they're chiral, I'm gonna draw every single bond that the possible chiral center is attached to. So if I'm looking at, let's start with this one. I'm gonna guess this is chiral because I see 3 different atoms attached to it. On here, I have a hydrogen, which would be on a dash here, and then I have a CH3 and a CH2 on this side. So I want to know whether this is chiral or not. So let's start with looking at our groups. It's extremely similar to the one we had over here. Actually, it's the exact same one, but I start with the top. It's going to be my first group, and then it's my hydrogen's my second one, and then we just went over this. This one, although both this carbon and this carbon are both just carbons, one is attached to 2 hydrogens going up and down, and one is attached to 2 hydrogens and the carbon, and this one's just attached to 3 hydrogens. So those are different groups. So that's my third, and this is my fourth. So this one is chiral. So I have the chiral center here. And then I come over to this molecule and try my same process. So I see at least 3, I see 4 atoms connected to this one. So let's check to see if these are the same groups. I'm gonna write in my hydrogen here, and I know that this is an assumed carbon with 3 hydrogens attached to it. And then we can move over to this one. It's also a carbon with 3 hydrogens. And then our last group is a CH2, so 2 hydrogens attached to it. Looking at these ones, I'm going to start by addressing my first group. So I have a carbon and then attached to 3 hydrogens. And then I have a oxygen, that's my second, a hydrogen, that's my second one. And then I'll come over here and see that I have a CH2 that's also going to be attached to another CH2 and then a CH3. So that's going to be different than this one, even though they're both carbon. This one's attached to a second carbon, and this one's attached to 3 hydrogens. Now I come over here and kind of look at what groups I'm attached to. Going up, I have a hydrogen, and then to the side and this other side, I have hydrogens as well. So CH3, and then if I look at my other groups to make sure that I don't already have a CH3 listed as one of my different groups. So I can come over to this carbon, and I already have a C with 3 H's attached. So I know that both this one and this one over here are both the same group. And I can't have a chiral center when I know this is the same group and this is the same group. So this molecule is not a chiral center, and this molecule is achiral. So then I'll come over to my last one. This one's my ring. And rings are the ones that are definitely the most tricky when you're deciding whether it's chiral or not. The reason for that is because you can keep going around and finding different things. But if you don't ever find a point of difference, we need to check to see if those are chiral. So I'm going to come over to my bond over here because I have 3 different atoms that I know I'm attached to, or 3 parts. So I have a hydrogen here. I have C with 3 hydrogens here. And then on this one, I have a C with 2 hydrogens. And on this one, I have a C with 2 hydrogens. So I'll just write that in too. So in this one, I'm looking at my different groups as well. So my first one is my hydrogen. No other groups are even H. I have 3 groups with just C's attached to, but I know this is CH3 and the other 2 are just CH. So I know those are different. And then I'm going to check whether these 2 have a point of difference in them. So I go to this one and I have a carbon attached to a hydrogen and a hydrogen. That's the same as a carbon attached to a hydrogen and a hydrogen over here. And then if I go out one more, I have a carbon again and a carbon again. So to this point, I know that I'm not chiral yet. So I'll come out to this spot here to see if there's a point of difference in this spot. So then if I look at these 2, H, H, and then H, and H, and then I'll even drop for these 2. Now both of these ones, I'm going out to see if they're different again. At this spot, I have another carbon just attached to 2 hydrogens. So this one can't be, this whole group is going to be the same as this whole group, which means that I only have 3 different groups attached because this is the same group as this is. So I know that this one is achiral as well. So I'll draw my X, and this is achiral. So I'll keep going down to my enantiomers and diastereomers. So we know enantiomers, the definition of them is a non-superposable mirror image. So that means that when I'm looking at them, I'm going to have 2 bonds that are just flipped. So in this example, I think the easiest way to draw enantiomers of each other are to keep them exactly the same and just flip the wedges and dashes. So my oxygen staying in the same place, my amine group is staying in the same place, my hydrogen staying in the same place, and my CH3 over here that is assumed is also staying in the same place. What I did change is my wedges and dashes. So here I had a dash and now it's I had a wedge over here and now it's a dash. And over here I had a dash and now I have a wedge. So that's the easiest way to tell enantiomers. I know they're immediately enantiomers of each other because the hydrogen was on a wedge and now it's on a dash, or vice versa. And the CH3 was on a wedge and now it's on a dash, or vice versa. So the easiest way is to just look at if my molecules are in the same point of difference from each other. So like N is still directly next to O and C, and then C is still next to N and hydrogen, and oxygen is still next to N and hydrogen. None of those changed, and they're flipped, so they have to be enantiomers. The other way you can check is by doing R and S conformations. So I know that enantiomers are going to be flips of my R and S conformation. So if I'm drawing something with like this, we already talked about this is a stereocenter, and this is going to be on a dash. And then I look at this one. Oops. I draw my same molecule, but now instead we're going to put it on a wedge. Actually, I'm going to switch it up a little bit. We're going to put it under here. I want to know if these two are enantiomers of each other. So the easiest way to do it is to find R and S of each other. This, in my personal opinion, especially if they're in a line drawing like this or a Fischer projection, the easiest way to find it is do R and S of them. So R and S follows a few rules. The first thing I'm following is what is the heaviest. So if I'm looking for priority, that's the first thing we're going at. I have a carbon. If I look at the periodic table, I know the atomic weight is about 12. If I look at oxygen, I know that the atomic weight is about 15.99. And then my hydrogen is about 1.0. So when I'm looking at all these, I know based on the periodic table, which you'll have on the exam, oxygen's gonna be the heaviest. Now I'm coming to my second group. Based on looking at them, I also know that this carbon and this carbon, they're both carbon. So they're both 12. But I also want to know what like the bulkiest group is too. So I want to know, is this one going to be heavier than this one? So this one has 3 hydrogens. So if I were to add like 12 plus 3 times, plus 1 times 3, or if I come on this side and go, okay, I have 12 plus 2, and then plus another whole 15 over here, because I have another carbon attached instead of just 3 hydrogens. This group is going to take my priority. And then hydrogen is the lowest priority because it's the lightest. So in that case, I know that my priority is going to go 1 to 2 to 3. So the way I'll draw that is like this. And does anybody know, is clockwise R or S? Man, is everybody like tired today or like really silent?
What was the question again?
Is clockwise R or S confirmation? R, correct. And the reason that the way you can remember that is right is R. So I'm coming to the right, that's R. And then S is just the opposite direction. So R is right. But now I have to look at if my lowest priority group is in the back. So I know this is an R right now, but also I have my oxygen in the back, which is my highest priority, which can't happen. And my hydrogen, which is my lowest priority, is the front. So what I have to do is, if I had a model kit, you have to rotate your whole thing so that the hydrogen would be in the back. Honestly, you have like nothing on the exam. There's not really going to be, unless you change something, there's not going to be anywhere you'll have to really look at it in 3D. But if looking at it on paper, you see a hydrogen on a wedge or just anywhere that's not in the back, just immediately know it's the opposite. So we said it's R, which according to rotation it is, but we have to move it to S. So this is actually an S confirmation. Now let's look at the same one over here, where we want to test to see if these two are enantiomers. So I'm going to do my priority list again. It's the same thing. Oxygen's number 1, you're number 2, he's number 3, and the hydrogen here is going to be number 4. So let's see if this is the opposite. So we want our enantiomer to be R confirmation because over here it was S. So if I do the same thing, I have counterclockwise, which is S because we just learned. And then let's see, is my priority groups in the front, my hydrogen's in the back, which is my lowest priority, and then I have CH2 and CH3. So this is all good. So this is also an S confirmation. So I'm not going to change anything. So these two are not enantiomers of each other. They're actually the same molecule. And if you're the way we did R to S here, this is actually what we do. You would just flip it around to make it in this confirmation if you're trying to flip it to the proper thing to get your priority group in the front. So that's why it's so important to remember where your group is, because if I were to move my OH up to the top and keep it on a wedge, now my priority it's the same priority, but it's a different spot. So it's 1, I'll keep it blue. It's 1, 2, and 3. And then I have an R with flip, which will stay R. So these two would be enantiomers of each other. Instead of the other one we saw just S because it had to flip, but these two are not. So these two would be enantiomers. The other thing we have is diastereomers. I feel like a lot of people kind of miss this concept. I don't know if like what happened, but there were a lot of weird things going on in the last thing when we were doing practice problems, and I feel a lot of people miss this. So diastereomers is not, we can't always, when we finish like a reaction when we get a racemic mixture, we often will have just an enantiomer as our other product, but that's not always the case because we can also just have a diastereomer as our product. So diastereomer is the flip of one stereocenter, but not the other. So if I look in these two, both of these have stereocenters. This has 2 here, and this also has 2. So this one is going to be an enantiomer here. Oh, whoops. So if I look at it, for the one that actually flipped, I know it's going to be 1, 2, 3, which will produce this. And that would make it S. And the lowest priority groups in the back. This one would still be 1, 2, 3, but it will actually flip to R because the lowest priority group is not in the back. So can I safely say these are enantiomers of each other? So it went from RS to R, but are these enantiomers of each other? Are these molecules enantiomers? No. Yeah, someone said in the chat they don't completely flip. The reason for that is this one flipped, but this one didn't. which means that these are diastereomers. One flipped, but the other one didn't. So if you are about to write plus enantiomer on the exam, I would just draw it out because it's easier. And you'll probably also get a question like this. We had one on the practice exam that looked similar, where we're wondering if they're enantiomer with each other. Another thing we have is meso. We like barely covered this in class because that class went long, and then Dr. Barrett just shouted it as people walked out, and I don't think anyone's paying attention. But meso is going to be something where we have an internal plane of symmetry. This means that when I'm looking at it, I have stereocenters here. So this is a meso molecule here. I'm looking at it and I have stereocenters here. There's one here and there's one here, mostly. A better example would be this, actually. I have one up here and I have one down here. So now I have to look at, is this, so this one's a stereocenter and this one's a stereocenter. So is this molecule chiral? And the answer is no. And the reason for that is if I were to take a mirror and draw and put it right between that molecule right here, I would have the exact same thing on this side and on this side. So now the question is would that be the same if I had this product? Whoops. So is this still meso? And it's no, because on this side, I'm facing down and this one's facing up. And over here, this one's facing up and this one's facing down. So these are actually not meso because one's going down, one's going up, the other one's going down, the other's going up. In case anyone's wondering, I actually had a question that was almost that exact molecule in the ACS, so I would remember that. So now we're going to look at the most stable conformation of a chair. So this was another thing that I feel like a lot of people get confused on is chair conformations, but they're actually not too bad. I'm going to bring down this thing. Whoops. So this is going to be your chair conformation every single time. So I know that a wedge is up and a dash is down. So wedge is up, dash is down. So when I transfer that over here, I want my wedges to be going up. So in one of these spots, I'll do it in green. So up or up here or up here or up here or up here or here. Those are all up spots for me. So those are all spots that I could put anything that's on a wedge, like here and here. Dash means down. So if I'm looking to put something down, I could put it here, or you get the picture, any of these spots. So when I'm looking at this, I want to see where is the most stable place that I can put my wedge here and my wedge here and my dash here that I will get the most stable conformation. So this is where we're going to have our chair conformation come into play over here. For as far as equatorial and axial, I know, trying to get rid of that. I know that this side here is going to be, all of these are equatorial because they're not just going straight up and down. They're actually kind of coming out toward us because they're on the sides of the molecule and they're away from like the big like carbons and the other substituents that are coming off them. So if I have a bulky group, I definitely want to put them equatorial each other because we're going to have less steric hindrance. So when I come over to this molecule, I want to find how I can translate this molecule onto this chair conformation in the most stable way. So what I can start doing is I always want to start labeling my carbons. This doesn't have to be in any priority rules. You just pick anywhere you want and just stick with it though. That's the important part. So I usually just start counting from the top. So I'll go 1, 2, 3, 4, 5, and 6. So I always start from the counting from the top. And then on the other side, I like starting counting over here. I don't know, it's just personal preference. You can go anywhere, but you want to put numbers on everything. So now that I'm looking at it, I want to move all these to over here. So the only thing I really need to keep consistent on this is how far apart the groups are and to keep them facing up or facing down. So this group is up right now. It's on a wedge, so I need to put it in up position. I labeled it as carbon 2, so I need to put it in an up spot. And I'm actually gonna change my numbering just a little bit so that we get a little bit more of a good example. So we're gonna ignore what I said a second ago, but we'll start by just putting this on the number 1 carbon. So I put this on the number 1 carbon. So on here, it's gonna go up and to the side. It has to be axial here because I know axial has to be up, or up has to be axial in this position. So if I want to put my number 1 here, the number 1 in the up position has to be axial. That's just how a chair conformation works. So I'll have it going up, and then it doesn't matter if for the second one, if you want to go that way or that way, but you want to indicate that it's attached to something else there. On my number 2 carbon, I have something facing down. So if I look at number 2 and down, it has to be down. I look at this carbon, this spot right here, and then my down is axial, and then my up is equatorial. And I'm down, so I have to put it in the axial position. So down is right there. For carbon number 3 on both of these, this is also up. So I can come back to my thing and then go, okay, on carbon number 3, this has to be up here, and then equatorial's down, and I'm up, so it's gonna be axial. So it'll be up like this. Now I have to know, is this the most stable conformation? So if anyone who knows, is this the most stable conformation of the chair, or is there a way I can put this on the chair that's gonna be more stable? Yeah, so someone said, couldn't you spread out the substituents to make them more stable? So I can't spread out on the number of bonds. So this has to stay, I think I know what you meant, but I can't say that this is gonna be here, or like that these methyls are gonna be more than one carbon away from each other. However, there is a more stable thing that I can do that's gonna rotate these carbons into a more stable place, which is going to be the equatorial spots, which I can see everybody is now saying, yes, equatorial. So we're going to do a chair flip. The way we do that is we're just going to rewrite. I like to write a completely new chair, and we're going to move all of our carbons just one bond over. The one thing we have to make sure in our chair flip is I'm not changing up or down. So everything on here is going to stay either up or either down. So this was up before, so it's going to stay up. This was down before, so it's going to stay down. And this was up before, so it's going to stay up. So when I come onto this one, we can start our numbering again. But I want everything to move one. So I started my numbering here last time. So I'm going to move it down here this time. And then go 2 and 3 and 4 and 5 and 6. So in my number 1 spot, we have our ethyl group, and that was facing up. So I'm going to come onto here and see that on this carbon, my equatorial spot for number 1 is going to be up. So I'll go 1 and 2 for my ethyl. And then on number 2, I have my down methyl group. So down on the number 2 spot is equatorial. So I'll come like this, and that's down now. Number 3 on here was up, and this will be on this carbon. So here up is going to be equatorial. So I'll go like this. And now if I look at this version of my molecule, this is like 10 times more stable, because before I had this going like close to all these hydrogens, and it was really interfering with all of my stuff. But over here, my molecules really spread out, and my big groups are going to be equatorial. So that's what a chair flip is. We're just moving everything one so that we're getting it into a better position. The other thing you can do is you can flip every single, if every single bond was up, you can make all of them down. So like this chair is the same, or this cyclohexane is the same thing as this. So these are the same two. I can do a chair flip in the same way. I don't recommend doing that because there's a way that you can just do a chair flip like this and just move all of your bonds one, and you're totally fine. So yeah, that is the two ways that you can do that. So now we're going to get into some Newman projections. So someone asked me to do the one we did like in class the other day. It was, I'm trying to find it. So the question gives this. So before we start a problem, I'm just gonna give a general overview of a Newman projection. A Newman projection is written by this really annoying guy named Newton or something, because I hate doing these. But the idea is you have all of your, you have two of your bonds that are next to each other. Like this circle is going to be one of our carbons, and this dot in the middle is also a second carbon. And we're just trying to draw it in a way that you can see it well. So there's a few ways I can draw my Newton projection. I'm not going to go all of them because the ones that you really want to know are gauche and eclipse. So I drew this in a gauche conformation, because all of these, if these were all CH3s on the end, this is going to be, they're pretty far from each other, which is going to eliminate that steric hindrance we talked about with chair flips. But if I have it where suddenly, for some reason, this rotates and these are on top of each other, this is called an eclipse conformation. I think of it because I'm looking at the moon and it's eclipsed over the sun. It's an eclipse, same thing. They're right on top of each other. And I have, this is like not stable at all. So in a situation where I have like CH3 here and then CH3 here, this is going to cause a good amount of steric hindrance. So it's better for me if I use my gauche version of this. So the way you can write these, and now we'll do our problem, is someone did this molecule. Nope. If I can find it. I might have deleted it. No, I didn't. So if I have this molecule, then I want to find, and the question asks, what is the most and the least stable conformer in a Newman projection? So I have a few ways that I can start. I'm going to start by drawing, when we're looking at this carbon from a like 1, 2, it would be 1, 2, 3, 4, and then we're looking at from 5 to 6. So if I have 5 is my like closer one and 6 is my back one, then that's how you would look at it. So 5 would be that one and 6. So I'll start by drawing 5 in the back. Whoops. And then 6 will be in the front. So I'll draw that in purple. And then now I have to find, and I'm drawing the most stable. And I drew a gauche conformation because I want this to be the most stable, and gauche is more stable than being eclipsed. So when I have this conformation, I want my biggest, my bulkiest groups to be anti from each other. And I think about it as a big scale. So I want as much as possible. If I have like 100 pounds on this side, then I want as much weight as I possibly can put on the opposite carbon, anti from it. So if maybe I have 125 pounds. So I want these to be anti from each other because I want them to be opposite to balance the molecule out. So in this example, I have two really bulky groups. On this one, I have a bulky group that's CH2, CH2, C, and then CH3, it's an isopropanol. So if I look at this, I'm gonna go, okay, I have 1, 2, 3, 4, 5 carbons on here. Or I can, if you're looking at it as like big weight and how bulky it is. So if I'm looking at weight, 1, 2, 3, 4, 5 carbons, all of these are carbons, so I'm just looking at that. So as far as weight, I want this first carbon to be the closest, to be one of mine. So CH2. So that's going to be pretty big. So I'm going to use that one first. And then I'm looking to put on the bottom, I want to find my second biggest group, or my biggest group that's on this carbon. And on this one, this is definitely my smallest. This is my second smallest. And then I have this one that's going to be my biggest on this carbon. So I have CH3, CH2, CH2, CH2. Well, it should technically be like this. So those two are going to be my biggest groups pulling away from each other. And then for my other ones, I'm going to put my hydrogens anti from each other because I have two hydrogens. So both of them are pretty light, so I want to balance that out. And then my other one is I have my, on my purple carbon, I have a propanol or propyl. So it's CH3, CH2, CH2. And then on my other one, I just had an ethyl, CH2, CH3. So this is going to be on most stable because my biggest groups are anti from each other. For my least stable, I'm going to have a reasonably similar Newman projection because I'm trying to put my biggest groups. So if I'm looking for least stable, my least stable would be a lot of steric hindrance. So my least stable groups in this are now going to be right next to each other. So this is my eclipse conformation, and I'm going to put my biggest groups next to each other. So my first biggest group was this big one over here. I'm just going to copy and paste it. So this was my biggest group, and it was on my purple carbon. Oh God. It's on my purple carbon, so it'll be here. And this was my second biggest group, or this was my biggest group on my blue carbon. So I'm going to put that one up here, and I'll make this line to it better. And then I had my second ones together. So hydrogen is also going to be paired with hydrogen because they're both pretty small. So they're not going to produce a lot of steric hindrance, but we're just looking for our biggest to match up with the biggest, smallest to smallest, and then our medium groups together too. So for our medium groups, we had our propyl on our purple carbon, and then our ethyl on our blue one. And this is going to be our least stable. So we have our most stable on our left and our least stable on our right. This is another kind of topic you're going to want to know because I had to draw something like this. I will note, I said earlier that we're looking for the biggest atomic mass. The reason I said that is because we're looking at only carbons in this case, but typically you're going to look at the first one that it's attached to and ask about that one and then move on to the next one. So for instance, if I had bromine as one of these instead, bromine, if I'm looking at my least stable, bromine is heavier than carbon. So this one is going to be less stable. So I want to put this one because bromine is a good amount heavier than carbon. So it's going to produce more hindrance than carbon. And then if you do have that tie, that's when you're going to go to the next one, which is why that is the case. That's Newman projections. And now, what was my next one? Fischer projections, that was it. So Fischer projections are going to be, I hate Fischer projections personally, but you do also have these on your exams. So these ones are just saying that if I have this, and I'll just put a few things on here, OH, and then H, and then OH, and then on this side, I had chlorine, I don't know, bromine, and then let's put hydrogen. And then let's put CH, an ethyl group over here. So in this case, what I'm looking for is how I can turn this into a, it's like a, just, it's 1, 2, 3, 4, 5, 6 carbons. So I'm just looking to see how I can turn this into my straight chain of my ethyl. So with 6 carbons, I'm going to 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 5, 6 carbons. And then I had on this side, if I want to number these, 1, 2, 3, 4, 5, 6. So we'll label them again, 3, 4, 5, and 6. And this labeling doesn't have to be in priority. I'm just trying to keep it consistent as I move it from one to the other. So on carbon 3, I had an oxygen. And does anybody know, is this going to be on a wedge or a dash? As people figure that out, I'm going to keep putting my stuff on here. So I'm looking to find the stereochemistry of each one of these because my Fischer projections do give me stereochemistry. So I want to make sure that I keep that consistent as I'm moving from my Fischer projection over into my hexane chain. And this is kind of a hard thing to figure out. I'll wait a few more seconds to see if anybody has any guesses. Doesn't look like it. So we'll just try to solve. Do you remember I said a little bit earlier, R and S is our easiest way of determining which things are, how to kind of figure out if enantiomers were real. It's going to be, or if enantiomers are actually enantiomers, it's going to be the similar here because I want to know if I find the R and S of each, I know my stereochemistry going from my Fischer projection to my chain has to remain consistent. So what I can do here is start finding my priority. So oxygen is lower priority than chlorine. So you're number 1 here. And then my oxygen's number 2. And then I'm comparing this carbon versus this carbon, but this carbon's attached to a bromine. So this carbon is going to be my 3rd priority. And then, oh, my bad, I didn't mean to do that. And then my 4th priority will be this CH3. Now, this is something important to note because when I'm looking at these 4, I don't just want my hydrogen to be in the back, I want my lowest priority group to be in the back. And in this case, it is, so it's not a great example, but if this were to be, if this CH3 were to be on one of these side things, because when we're looking at this, we are looking at like a bow tie. So I know that this is what a Fischer projection actually looks like. It's saying that the 2 that are horizontal are coming toward the front and the two that are vertical are in the back. So when I look at this, I'm looking at like my bow tie kind of thing, and I want my lowest priority group to be in the back. Whoops, so I'll keep that there. And now let's do RNS. So 1 to 2 to 3, so it's gonna go like this. And we said earlier, this is R then, and our lowest priority again is in the back, so we don't have to flip as far as that goes. Now let's take a look at our second one. Bromine's our highest priority, it's the heaviest. And then if we're comparing this carbon, they're both CH, so we have to decide which one is better. Actually, this is CH and this is not C, but this one is attached to chlorine, an oxygen, and a CH3. All of those groups are going to be heavier than like an oxygen and a hydrogen compared to and a carbon. So this group is better, so this will be priority number 2, which means this is 3 and our hydrogen's 4. So now we're going to do our same thing. So bromine to our second priority around to third. This is also going to be R, but now we have something to consider. Remember we talked about a second ago that both of these are on wedges and dashes. So if I look over here, this hydrogen is on a wedge, which means my lowest priority is not in the back. So instead of this being R, like we just found out it should be, oh, my bad. This is actually going to end up as an S conformation. Oops. So this is S, and now we'll move to the last one, priority number 1. Priority 2, again, this one is attached to a CH and a bromine, and this one is a CH2, CH3, so this is better. And then 3 and 4. So we're going around like this. That's going to be an S conformation. But again, our hydrogen's in the front. So it can't be that. We got to move it to the back. So this will also be an R. Now I can come across to my other side over here. I said that on carbon 5, this was in an R conformation. So let's see how we can make that an R. So chlorine is my highest priority. So if I were to do it, I go 1, and then 2, and then 3 over here, and 4. And that would produce, if my highest priority was in the front, my lowest priority was in the back, that means that this would be in a S conformation. Let's see what it was before. Before, I had it in R. So the way that I'm going to have to change this is by putting my priority group not in the back. So what I can do is make my chlorine in the back, and my lowest priority will just go in the front. The CH3 was the lowest priority, so let's put it in the front. Now I can check, because it's still going to be in this. I'll undo that. I'll put that back for a second. It's still going to be in this rotation that should be S. Wait, is that R? Wait, is that R? Sorry, that's R. So it was right. Never mind, everybody. So if this was correct being chlorine in the front, or if it was in the front, so I'll put this in the front and my lowest priority in the back. So I know this is R, and we're all good here. Now let's move on to my second carbon right here. Before, I said that this carbon was an S conformation. So I need to make sure that how can I keep it as S? So I'll put my hydrogen in as well, and let's look into it. So I have priority number 1, priority number 2, number 3, and number 4. So if I go like this, that's going to be R again. So I have to put my hydrogen in the back, in the front. And then I'll put my bromine in my back, and then that's going to keep this in a S conformation. Now let's move on to the third one. This also has a hydrogen coming off, and we also want it to be R. So I'm going 1, 2, 3, and 4. And then I go like this. That's going to be S. So I need to make it R. So what I'll do is put my main group in the front, in the back, I mean, my priority group in the back, and my lowest priority group in the front, and that will rotate this to an R conformation. Now I know that this is the hexane version of my Fischer projection. So that's gonna be how you do both, you draw this, but my hexane chain, as well as how to find the R and S of a Fischer projection. The only other thing that Fischer projections can be used for is to find enantiomers for. So if I was comparing that Fischer projection to basically the same thing, but if you want to move around a few molecules and say this is over here, then I'm going to look at this because this was R before. I'll just check to see what it is now. I know it's 1 and 2 and 3, and then that is going to produce S. And all my lowest priorities in the back. So that's going to be S, which I know would be what it would be without, that would be an inversion. So this could be two options here. So if I'm looking at these two, are these two diastereomers or enantiomers of each other? And I'll wait for somebody to let me know. Yeah, somebody said diastereomers. That's exactly right. Because this one flipped, but I have two other stereocenters here. This one didn't flip, this one didn't flip. So no, they're not. However, I could have it where if I flip these two as well, and these two, now if I look at it, I got 1, 2, 3, and around. That's R, S, and we're flipping to R. So this is R now, and just take my word for it, the other one's going to be S. This would be the enantiomer. So if everything I'll rephrase, if every stereocenter flips to having one on one side and one on the other, then that's how you can check for stereocenters. The one thing you might see on the exam that is honestly pretty likely for you to see is if like this part flips too, where she moves like a bottom piece. Just use your R and S, find to see whether that's a stereocenter or not. It'll take you a few seconds on the exam. Just when you're doing that, you just want to check, are my lowest priority groups in the back, and did all my stereocenters flip for enantiomers, and did at least one flip for diastereomers? I can guarantee you a question like that will be on the exam. So that's Fischer projections, and now we can get into everybody's favorite reactions. So we'll start with an SN2 reaction, and we know a few things about SN2. So I'll write that up here. And SN2, and just things we know about it, is that it takes place with a strong anion. We also know that it works with primary or secondary carbons. We also know that it produces an inversion of stereochemistry. And you won't really get too much into this until after the exam with elimination, but you are using a weak leaving group. Oh, sorry, strong anion nucleophile, my bad. Weak leaving group. That's for SN2. That's the things we know about it. As far as the mechanism goes, you'll start with the option to make a better leaving group. That can happen. Some of the stuff I'm gonna do will probably be like an example of what you might see on the open-ended of some of these reactions where you're gonna draw out your whole mechanism. But for SN2, you know you want the first step is gonna be to make a good leaving group. So that is not always the case that you have to do that, but it can happen. We'll go over an example where you do have to make a better leaving group. And the second step is going to be our heterolysis / our coordination. Does anybody know what heterolysis and coordination mean? One is bond breaking and one's bond formation. So just what is both of those? Yep, someone said heterolysis is bond break. Coordination is bond formation. So whenever we're drawing our mechanism, we're just making sure that we're doing bond break and bond formation. And in SN2, it's a concerted mechanism. So now let's try an example of this. This will just be a pretty simple one. Oh, actually, I'm also just going to give you a few recommendations for some possible nucleophiles that you'll see on the exam. One nucleophile you could have, common ones are going to be OH minus. That's the conjugate base of water, which is why you're seeing it. SH minus is a common one. NH minus is also, or NH2 minus is also a common one. You could have like, and this is going to be the same thing as as OH minus, but like NaOH is going to be the same thing. And what a lot of people don't realize is also KOH, also the same thing. So whenever you don't have just a regular anion, you don't see your negative charge. By the way, just anion means negative charge, cation is positive charge. The way you think about that is cat is positive, like PAW. I know it's a pun, but now you'll never forget it. But the way you're going to tell is you'll have a periodic table in the exam. If you're ever not sure if you have one of your like strong anions, the way you can tell based on not seeing a negative sign or not doing a proton transfer step to make a good leaving group is going to be look in your first group, group 1A in your periodic table. That group's called your alkali metals. And all of those will produce a positive charge when they break apart and make the other one negative. So in the example of these two, Na plus is what you're actually seeing and O minus is what you're actually seeing. So that's something. Also K plus and O minus, same thing. Both of them are alkali metals, so they're just going to make the other one negative. And what that's called is a conjugate base. So like nucleophilicity is a conjugate base. I don't know if this will be the multiple choice section of your exam, but another thing to remember is just on your periodic table, nucleophilicity increases going down the periodic table and to the left. So for instance, nitrogen is better nucleophile than oxygen, which is better than fluorine. And then also like sulfur is better than oxygen and stuff like that. But those will be your three most common nucleophiles. The other thing you could see is a Grignard's reagent, which is going to be your Mg, like MgBr. And then you could have like CH3 on this side. That just means that there was a carbon that the MgBr will break off and it will produce this. That's called a Grignard's reagent. It acts as a good nucleophile. Your other one you could see is your lithium. I think it's called the lithium halide specifically, but I could be wrong for sure. That would be like, we'll give the same example, CH3 Li. What you're actually seeing there is this. Same exact thing, gonna happen in the same way, but just remember lithium won't, when you see lithium, you're not actually gonna get that group. This is a really important thing that she definitely didn't, I feel like that I wasn't told last semester. That both lithium or that like MT or sorry, my bad. ME stands for methyl, and ET stands for ethyl. Another one you'll see is tert, butyl is this. And on the other side could be anything. It could be O minus. That's a really good nucleophile. That's something you could see. But tert butyl is just this group. So for instance, a way you could see that is MEOH. It's methoxide. It would be this. ETOH is ethoxide, like this. And then I gave you a tert butyl example, and this would be tert butyl. So anything like that, just be prepared that you can see some weird things. Another just tip for taking her exam is when you're looking at a few things, or when you're looking at your like reagents, just look for what you know to be a good nucleophile and what you can use to make a better leaving group, not particularly what I have to use to like you might see something like DMSO as your solvent. You could see something like this. And then like this in a reaction like this. So in this case, just know you're not actually looking for your like this DMSO can look really confusing. It stands for dimethyl sulfoxide. It means nothing. It means it's a solvent. You might use it next semester. It just means it's a solvent though. You're not actually worried about that solvent until on the next exam you might have a few that involve DMSO that you just have to remember. But don't focus on this part. Focus on the top. I know what the top does. What am I going to use with that? Especially in a lot of your synthesis problems. She loves those. Look for the things you're going to use and the things that are going to be acting as, and then the things you need to ignore. Like if I see like OH DMSO is step 1, and then step 2 is like HBr, that's you won't have anything with that, but, or this is a better example, like BR2 and UV, that is going to be the same thing. That's going to produce, all I'm looking at in this case is just you, and you are the only thing I care about. Just so you know, a free radical, I don't know if she said in class, but free radical usually needs some sort of energy to take place. So UV light is a very common one that does count as like an energy source. So BR2 and UV light go together well to make a free radical reaction, which could add on somewhere here. Okay, so now I'll continue with actual SN2. So we know we need to make a good leaving group, and then heterolysis / coordination and protonates neutral. Those are my 3 steps. So let's try one. I'm gonna put one of these on the board. This is pretty simple with bromine, and then I'll do this with SH-. The way this will work is I'm gonna either make a good leaving group or already have one. Actually, I'm gonna change my leaving group, my nucleophile a little bit, just to emphasize that these things are the exact same. This is plus and this is minus. Same exact thing. The Na is not going to do anything for me. Doesn't matter. My nucleophile is still this. So I have my nucleophile. Let's look for my leaving group. Bromine's a good one. And the reason for that is because bromine's very electronegative, which means it's partial negative. And that is making this carbon very electron poor. So it's going to be slightly positive. And I want to go from my electrons in the sulfur, and then I'm going to come and bring my electrons from the sulfur onto that electron poor site, because electron rich is moving to electron poor over here. It's going to attach here, and then my electrons in this bromine bond are going to break off, and then I'll get my product without that bromine bond, but with a new bond that is just SH. So up here, SH. Half the time you won't have to add this, but in case she specifically asks for it, you can write NABR on the side. And then this is a full valence shell. So that's a SN1 reaction. We went from electron rich over here because I have my negative to electron poor over here, and then it broke off. I'll just label what we did too. This is coordination. And this is heterolysis. And that's what we did. Coordination of the bond, heterolysis, and then we produced our SH on the end. Let's try another one. And then I'll leave this one for a little bit and let you guys do it. And then just when people are done, let me know, and then I will do it as well. Oh my gosh. There we go. H2. And then so I'll leave this one for a second, and then just someone send something when you're ready. Yeah, someone posted they were done, so I'm going to start doing it. So we're moving from, I know because this is my one of my alkali metals in my first row of the periodic table, that's going to be positive and that's going to be negative. So this is very electron rich. And then iodine is a good leaving group because it is very electronegative. So it's I minus or partial negative, and that is going to make the corresponding carbon very it's going to be partially positive, and it's very electron poor. So what will happen in this case is nitrogen has just one set of lone pairs here. And what will happen is it's going to come in with coordination. And then in this case, we're going to see heterolysis. I'm going to kind of simplify that. And what we'll see in the end is NH2. And this will have just one pair of lone pairs. And that's going to be our reaction in that case. So now we'll head on to ones that don't. So this is the case where everything you're looking for is exactly where you expect to see it. But that's not always the case. You can often have things moving in different ways than you would typically expect. So let's try another one. So I'll leave this for a little bit, and then you guys can solve it as well. It's been a little bit, so I'm going to go ahead and start this. So in this case, this is our Grignard's reagent right here. So what's going to happen is what we really know is here is this. Oh, my bad. Is this. Because that Mg is going to cause the Br to break off and that bond won't be there anymore. And then on the other side, in our reagent side, we had what our leaving group actually is. So CH3, and this is going to be our electron rich over here. And then over here, this is also electron rich, and this is electron poor due to that. So our leaving group, or our nucleophile, is going to come attached to our partial poor parts, and then our leaving group will leave. And what we end up with is this. So just don't always expect to see things where where they will, like, don't expect them to be always in the same place. Oh, I'm sorry. That's what it is. Because we grabbed the CH3, not the iodine. And then another thing we could see is just one thing to remember here is that SN2 is only going to occur with secondary or primary things. So if you're looking at it and it looks like SN2, we have a strong anion and it's tertiary, we're actually gonna have no reaction. That was a question I had that I remember. If it is SN2, so I have my strong anion, I have my good things set up to have a SN2 reaction, and it's a tertiary, it means that I can't actually do the reaction. So let's do one that is with opening epoxide. And this is going to start with, it's going to include my steps at the beginning and at the end that we had before of making a good leaving group and possibly protonating. So this structure is called epoxide. And it's an epoxide ring. That means this oxygen is the epoxide. We're going to have lone pairs here, and let's react it with CH3OH. So the first step in this is going to be making a good leaving group, and then we'll end up doing the rest of our reaction. So I'm going to start this, but what will happen is we know that our oxygen here is going to has its lone pairs, so it's gonna come. It's a pretty good leaving. It's a pretty good nucleophile. I mean, it's gonna come and take our hydrogen over here, and the electrons in this are going to break off and make our conjugate base of that. That's CH3O. So we did two things here. We didn't have a good base for SN2 here. And now we do. This is a very good nucleophile because now we are very electron rich here. The other thing we didn't have before is a good leaving group. In this case, I had like OH is pretty stable the way it is. So by protonating it, by moving this oxygen over here, I'm actually making a good leaving group as well. So what I'll be left in this case is this structure, but I will now have my hydrogen on it. And now I won't have that extra pair of lone pairs. Now we have to decide something. Our oxygen, because of where it is on the periodic table, wants two bonds, always. Two bonds every single time. In this case, oxygen is bonded to three things. One is the hydrogen, two is the carbon over here, and three is the carbon over here. And when it has too many bonds, it's sharing its electrons with more things than it wants to, making it partially positive. So now we have a good leaving group and a good nucleophile over here. Oops. So now we can do an SN2 reaction because we have both of those things. But the question is here, I can either break this bond where I can break this bond, and I'm doing SN2. So out of carbon 1 and carbon 2, which carbon do I want to break the bond from? And I will wait. Yeah, someone said 2. It is reasonably obvious because this is secondary and this is tertiary. I know that because I have 2 things that I'm attached to besides my leaving group. So I'm attached to 1 and 2, making it secondary. So I have to use SN2 on this one. This bond is too bulky for me to do an SN2 reaction on because it has so much stuff attached to it. So what happened is my nucleophile is going to come in and attach where that carbon is. And that's electron poor because this oxygen is pulling on it. And then this bond is going to break. What will happen now is we will get this bond to be broken. But we want to remember we're not taking off the oxygen completely. And the reason that is I only broke one of the bonds. This epoxide, or this oxygen now, is attached on 2 different things. Both this it was attached with this bond and this bond. And I just broke this one, which means that this one is still here. So I still have my carbon to OH bond. Now, if I look at how many things my stuff was connected to, this had 2 bonds before, or I'm sorry, 3 bonds before, and then 1 hydrogen. I had 1, 2, and 3. And now I just have 1 and 2. So this will be positive. It's going to be our cation because it lost a bond and in turn lost electrons. So what will happen now is I have, oh wait, I'm done, never mind. And then our nucleophiles here. But remember, oxygen brings it friends, so I'll also have my CH3. And that will be that reaction. So we'll do another one. I'm going to take one, an SN2 reaction that's in, we'll do SN1 first, and then we're going to do one with that is like modified from our practice sheet. We'll do a few from those, and then we'll be done. So for SN1, we have a few other things. I'm going to copy some of this. So SN1, for its nucleophile, is going to be a weak neutral nucleophile. And SN1 is going to produce a carbocation intermediate. So for SN1, I want it produces a carbocation. So I want that carbocation to be on the most stable carbon that it can be. And the most stable case in that is going to be like a tertiary carbon or a secondary carbon. So, but primary carbons are just too unstable for it to stable a cation charge. So I have to go with tertiary or secondary. In SN1, I have a reasonably the same steps. I want to make a good leaving group, and then I have heterolysis. And then I have my intermediate step of checking for rearrangement. And then my last step is going to be protonating to neutral. I'm sorry, 5 steps. Number 5 is protonating to neutral. And then I also have coordination. So some common nucleophiles that you'll see in SN1 are the conjugate acids of our nucleophiles for the other thing. So good base are strong, like we want a strong or weak base, or like a weak neutral base, I mean. So a good one is H2O, NH3, SH2, and then anything with like alcohol attached. So CH3OH, CH2, CH3OH, anything like that. So those, she put some of them on the board, but these are going to be your most common ones for sure. Anything that is going to be a like a strong base, or like, I'm sorry, a weak neutral nucleophile. So you're honestly just looking for the like acid, conjugate acid of the nucleophiles we used before. The other thing we're looking for is a strong nucleophile or strong leaving group. Again, we won't really talk too much about that until after the exam, but something like iodine is a really good leaving group because it's very electronegative. Another one is OTS. I don't know what it stands for, but OTS is a very good leaving group. There's a few other ones, but you're just looking for something that's very electronegative, and that's going to be your leaving group. It's a two-step mechanism, so we have coordination and heterolysis with a carbocation intermediate. And again, it produces carbonic cation intermediate. And then we have our mechanism over here. So let's go through this. So I'm going to write this like this. So this is ethanol. And what will happen in this is I know that OH is going to be my weak neutral nucleophile. And I'll have my heterolysis of leaving group. I'm going to abbreviate. And then what will happen is I have a carbocation intermediate. And that's because this had 4 bonds and now it only has 3. Next, I'm getting my ETOH. And I'll draw this out. It's just this. And what this will do, first we have to check for rearrangement. Is there anywhere on this carbon that is more stable than tertiary? No, there's not. So I would be looking for, this is tertiary, so I can't really get more stable than that, but that is something I'm looking for. If it's secondary, we're looking to check for rearrangement. Now the OH is going to come in and fill the spot that the bromine left. So I'll draw that in. And now I have O attached and then H attached with it. And then oxygen is going to bring everything that was attached to it. And now this will have this. But I'm looking at this and seeing, okay, I have oxygen and it has 1, 2, 3 bonds, which isn't what it wants. So this is going to be positive. So what I can do with this is make my new, using my bromine that left, and this is fully negative. And then I'm just going to redraw my hydrogen a little bit further away, but bromine will come and take this hydrogen and push the electrons that were in that bond back onto the oxygen. And what will happen with that is this. And that's going to be our final product. Oxygen has 2 bonds, so it's happy. The bromine took the H, and now we're all good. So that's a full SN1 reaction. So just going back over what we did, we had heterolysis the leaving group. We checked for rearrangement, we were good. We had our coordination, and then we had to protonate this to neutral. That's also going to be called the proton transfer, whichever is more helpful for you. Now I'm going to do one in a ring. I'm going to do one that has rearrangement possible, and I'm also going to do one with a that's intermolecular. So we'll try with the ring. Actually, and we'll use that same, or we'll use a methoxide. So in this case, my nucleophile is my OH. It's already a good nucleophile, and this is a very strong leaving group. So I don't have to worry about any of that. Also, I know this is a weak neutral. The conjugate acid of this, or the conjugate base of this, would be my strong anion, but I don't have that. So it's just CH3OH is going to be my strong nucleophile. That'll be good for SN1. Then this is a very strong leaving group, which is also good for SN1. So what's going to happen here is my OH is going to come. I'm sorry. First, my leaving group is going to leave. And then what I end up with is my carbocation intermediate. At this point, I have to check for rearrangement. Is there, and I'll ask everybody, is there a way that I can get my carbocation into a better position? And I'll label my carbons to see where would be a better spot for this carbocation. Or what kind of shift can I do to get my carbocation into a more stable place? Doesn't look like anybody sees it, but we're actually going to do a ring expansion. This is one of our types of rearrangement, because over here I have a cyclopentane, which I can make into a cyclohexane using my ring expansion. So what will happen is my carbocation here will come in to this ring like this. And then what you'll get is a new cyclohexane. And then we're going to relabel our carbons. So this carbon here moved on to this one. Hold on. Yeah. So I'm now going to have on my number one, I'll still have my substituent. But if I look into these carbons, before I had, and then I'll label this one too. One second, actually. Sorry, this is going to be, I moved my methyl group. My methyl group was on 6 before, so it has to stay on 6, sorry. And now if I look into all of my carbons, we're looking for which one has less bonds than it did before. So if I look at this one, my number one carbon used to have 3 bonds. Now it only has 2. So this is going to be my new carbocation spot. And this hexane is much more like stable than my pentane. So this is going to be a better intermediate. Now what I can do, and before you, I had always thought that this could move on to here, or my question was that I could move this to here, but it takes a reasonable amount of energy for this to happen, and you don't have enough left to then do a second rearrangement to push this over here. So we're actually just going to end right there. Now, we checked for rearrangement and we did it. Now my nucleophile could come in coordination. And then I can add that. And the last step will be to check if I need to protonate to neutral. I had methoxy, so the oxygen attached and brought its friends, but it does have a hydrogen, which is going to make this positive because of too many bonds. So same thing we did before. My OTS, you could even use another, we'll use a second methoxy in this. This can come and grab this hydrogen and this will break off, which will protonate this to a neutral cyclohexane. And that's going to be our answer for that. The other two types of rearrangement that you can do, I'll just overview them here, are hydride shifts and methyl shifts. If I have a carbocation here, then I want it to move on to the place that is more substituted, which is this carbon over here. If I possibly can, I always want to do a hydride shift before I do a methyl shift. So here I have a hydrogen I can use. And this is much more substituted in this one. So my carbocation will move over and the hydrogen will also move over back to over here. And then we will get this. And my hydrogen that was over there is now on this carbon. In this situation, carbon only has 4 bonds. 1, 2, 3, 4. So when I have my carbocation here, I can't take, there's no hydrogens on this carbon that I can take. So what we'll have to do instead is a methyl shift. So that's the same thing. We're just moving around our bonds and we end up with this. And then we'll attach the nucleophile. So this is a hydride shift up here. And remember, we always want to do a hydride shift if we possibly can. Hydride shift first, and then a methyl shift. So those are your 3 kinds of shifts that you can do. The last thing that we can do is, we kind of did most of the thing. Oh, we'll open up oxide ring. So let's look at this. I have a H2O, which is a weak neutral nucleophile, and I have an oxygen, or I have epoxide, which is not a good leaving group at all. So we can do the same thing like we did before. I'm going to have my oxygen come. I'm just going to draw the bond. My oxygen is going to come take my hydrogen, and that's going to break this off. And then this will come and make a new one. This is my new structure of OH plus, because this has 3 bonds now. And then I also have OH minus over here, because we lost an electron. So what's going to happen now is before we did SN2, because we had a pretty strong base, or we had a strong anion, but now we don't have that. The other reason is, I mean, we have OH, which is good, which we could use for SN2, but our biggest problem here is I have a tertiary carbon over here and another tertiary carbon over here. So I can't use 2 tertiary carbons for SN2. They're just not stable enough. So what I'm going to do is break this bond, making this. And now my oxygen is stable here, but I have a carbocation here. Now I'm just going to check for rearrangement real quick. I have 1, 2, 3. This is tertiary. You can't get better than tertiary, and I'm not going to make a ring here. So I am all good to add my OH nucleophile. and draw my product. Which is this. And we're good. Oxygen has 2 bonds here in both spots. So we're okay because they both have 2 bonds, so they're happy. And then the last thing we'll do is an intramolecular. So in this case, we're not given like anything we can use. We don't have like a reactant that we're looking for. Remember, on these exams, you're going to see a lot of stuff you're looking for the things, but they're in places that you won't expect them to be. So here, our nucleophile is actually over here, and our leaving group is there. But the way we can do this is first our leaving group, we're looking, the nucleophile that we can use is a weak neutral nucleophile, which is suited for SN1. And then over here, I have a leaving group. So my leaving group will leave for SN1. And then I have a carbocation intermediate over here. So I'm looking at this, there's nowhere that this can really arrange. So I'm good to continue with my coordination. Here, this is going to come around and attach over here, which makes a ring. So what I can do is I know I have 1, 2, 3, 4, 5, 6, and then 7. But my 1 is attaching to my 6 here. So I'll make a cyclohexane. And then 1 is going to be next to 6, and then 6 had a methyl on it. So I'm going to have this intermediate, but I'm going to look again, and oxygen has 2 bonds here, or 3 bonds here, which is not okay for me. So I'm going to add my positive charge on there. And I will do this. So what I can do is I can have my bromine that we took off earlier come over and snatch up this oxygen or this hydrogen, and then the electrons in that bond will go onto the oxygen. And this is going to produce my final product, which will be a cyclic ether that is now stable with a methyl on the second carbon, or on the first carbon. The last thing I'll do is I'm just going to take a problem that you used on the practice exam and just redo it. And then I'm going to give you guys a bunch of time, and then we'll go through it. And this problem is something that you would probably see in the open-ended of your exam. Um, All right, I'm gonna leave this for a while, and I'll give you guys like 5 minutes, and then I will solve it. All right, so it's been about 5 or 6 minutes. So I'm gonna go ahead and start doing it. The first thing you want to do is label your carbons in order of priority. It was listed at the beginning that amine is the second highest priority. Alcohol is the only one above it. So we're gonna go, 1, 2, 3, 4, 5. So this will be a pentane. The other thing we want to note is that we have a methyl and a methoxy on this. Methoxy is going to, I don't know, it would be alphabetical of nothing after it or something after it. I think it would be something after it, right? We're going to go with that. 5 methoxy, and then it would be 2 methyl, and then you could do either 3 pentanamine, or you can do 3 methyl pent 3 amine. So that would be our regular name for it. Now we have to determine our stereochemistry. So the first thing we want to check is what our chiral centers are. We have 2 kind of candidates here, one here and one here. If I look at these, we know earlier this one and this one are both CH3, so the same group. So that is not a chiral center. But this one has a hydrogen coming off of it, which is a chiral center. So I'll keep that here for just a second as I do it. I have 1, and then this one is priority 2 because this is going to be CH, and then I have both a CH3 and a CH3 and a hydrogen, and over here I just have CH2 and 2 hydrogens. So this will be higher priority, and then priority 3 is over here, making this a R rotation. And then the hydrogen, the lowest priority group is in the back. So we're okay to stay as R. So I'm going to add in here 3R and then a dash 5. I don't know if it would be methoxy first or methylpentane first. I think it would be methoxy first. I just don't know the rules of alphabetical. The next thing we're doing is reacting this with a strong base and then ethoxy. So what a strong base will do to this structure is actually take one of the hydrogens, making that nitrogen negative. So I have NH and then H coming off. I'm going to do this black, sorry. And then I have my strong base. So I'm just going to do like B minus. And it's going to come take this hydrogen, and then the electrons are going to go into the nitrogen. And then I check to see how many bonds does my nitrogen have. Nitrogen wants 3 bonds. We know that because of the column it is in the periodic table. It has a +3 charge when we're like doing naming. So it wants 3 bonds. So this will be negative. And now what we'll do is react it with our ethoxy. So ETOH. What will happen here is this is going to act as our nucleophile, and this is actually going to act as our leaving group. So I have this, and what I can do is send a hydrogen over. I didn't think about this too well because this actually wouldn't work great to be the nitrogen, because typically what you can do is have the H come over. What we'll do instead is to have, I'll protonate this. So we can use another OH group to make, so OH isn't a good nucleophile, so we have to make it a better nucleophile. Honestly, for the strong base, we should have used the OH instead because that is a strong base. So that's what we'll do actually. No, that wouldn't work. Hold on, I gotta think. What we'll do is we'll just use a second ethoxy. If you have something like this on the exam, that's what you could do, is use like a second form of it, and then take have this one go over and take the hydrogen, and then have this come off. And then one of them is going to be your like anion over here. This will make this. This would make this, but it's okay because we just want our organic product to be the most stable. And then what that'll produce is this. Now we have our good leaving group and our nucleophiles. So I'm going to have, and then this is also going to be SN2 reaction because I have my strong base, my strong anion, and I have my like good leaving group, and this leaving group is primary. So this is going to leave, and then this is going to come onto that carbon. And what you'll end up with is this. And 1 and 2. Now nitrogen has its 3 bonds back. It's really happy. So this is going to be our product. So last thing we should do is name the product. So what we'll get is our priorities stay the same. Oh, those two won't be in it, but we will have we'll keep the same thing as 5-methoxy. And then now what we have is we have a substituent on the actual amine, and that's going to be an ethyl. Oh, and ethyl comes before, E comes before M. So I'll have N ethyl, 5-methoxy, 2-methyl, and then I still have my pent 3 amine. And the last thing we have to do is just add our stereochemistry to it, which it's going to be your priority number 1 on this carbon. So number 1, number 2, number 3, it's going to go like this. Amines in the front, which means that we're going to keep it as R. So it'll be 3R N ethyl methyl 5-methoxy 2-methyl pen 3 amine. And that's going to be everything. So study hard, everybody. I'm sure you'll do well on the exam. I'll post this recording into the, or I'll post a link of it into the group chat. Yeah, good luck with everything. Study hard. I would recommend just doing a lot of problems. For a lot of these that we did, we kind of skipped, or we did the full mechanism, but on the exam, you're not really gonna have time to do absolutely every piece of the mechanism. So if you can really start looking at SN like 1 or SN2, this one is a little bit more complicated because it's intramolecular, but it's gonna be really helpful for you to be able to look at a problem like this and go, okay, this is my starting material, this is my reactant, I'm gonna go straight over to here, which is my product. And I know that's my product because I've just done these problems. I've worked through Dr. Barrett's sheets, and I know I'm good to go. So again, good luck, everybody. I'll post this for all of you. And yeah, have a good night.